So now that we have a sense of three-dimensional space and how it works and how the formulas translate, it's time for us to look at vectors in 3-space. Basically, everything we learned about two-dimensional vectors, for the most part, extends to three-dimensional vectors. So a standard position vector is a vector that has its initial point at the origin. And that's true in 3 dimensions just as it is in 2 dimensions. It's just that drawing them is more difficult because you're trying to draw with this perspective here. So you draw from the origin to the point on the corner of the box that you're going for. The basic vector calculations apply with some modifications. So for example, if we have the components for the points, x1, y1, z1, x2, y2, z2, and then that vector is from point 1 to point 2. So in other words, this point is the initial and this point is the terminal. Right? You can tell that because of the way the arrow is pointing. Then you always take terminal minus initial for each of the components to find the vector. The coordinate unit vectors in 3-space are, so the coordinate unit vectors, that should set off a little bell in your head, unit vectors that are on the coordinate axes, right? So unit meaning they have a length of 1, and coordinate meaning they're on the x, y, z axes. Okay, so there are 3 of them. There is I, that we learned about already. And again, sometimes he has an arrow, sometimes he has a little caret on his head. But that's I. I is 1, 0, 0. Then there's J, like that. J is 0, 1, 0. And then there's K now. So K is the 3rd one. Let me draw it right here. K, oh, I forgot to put the little arrow on J. Sorry, I tend to do that a lot. So K is 0, 0, 1. Those are the 3 coordinate unit vectors. We will, by convention, use IJK to refer to them, and often we omit the arrows. I was just doing it. It's just kind of pretty standard practice to omit them. Everybody knows what you mean with IJK as a general rule, so I tend to forget to draw them a lot, and so does everybody. All right, the magnitude of a vector is its length, which is the square root of all the components added together. It's kind of an expansion of the Pythagorean theorem. A unit vector is when you take the vector and you divide it by its magnitude. That will be a unit vector in the direction of v. And then to add, subtract, or multiply, you just add, subtract, or multiply the components. Multiply by a scalar, I should say. Multiplying by, in other ways, is for another section. But multiplying by a scalar is how we do it. All right, so let's practice that in an example. All right, so we have points P, which is -3, 1, 0, and Q, which is 2, -2, 5, and R, which is 1, 4, 3. So we're going to find the components of the vectors V and W. Right, so V is PQ and W is RP. So let's start there. All right, so part A, I want to find vector V, which is from P to Q. So P must be the initial and Q must be the terminal, the way this is drawn. So that means that I want to find terminal minus initial. So Q, so 2, take away -3. -2, take away 1. And 5, take away 0. Right? This is Q, if you will, take away P. Right? We're taking terminal minus initial. That gives us 5, -3, 5. All right, there's vector V. Now for vector W, we're going to do the same thing. Here, I'll do it right here. So vector W, but this time it's RP. So we want to take P as the terminal and R is the initial. So we're going to take -3 take away 1, 1 take away 4, and 0 take away 3, which is -4, -3, -3. Right? We were taking terminal, which is P, take away initial, which will, assuming it was R, not Q. That's what we're doing. Okay, so we have part A done. So we know how that's going to be. So now part B, V plus W. So I'm going to take vector V and I'm going to add vector W to it. Oh, I should have boxed that in because that was an answer. Well, vector addition with 3 dimensions works just like it did in 2 dimensions. So we're going to take 5, -3, 5, and we're going to add to it -4, -3, -3, which just means you take 5 and add -4, -3 add -3, and 5 add -3. So that's 1, -6, 2. Simple as that. Although I'm now worried about having enough space to do all of this. All right, C. Let's put C right here. -5W. Oh, that'll be easy, because that means you're just multiplying the scalar -5 times vector W. So -4, -3, and -3. That won't take too much space. So you multiply each component. So -5 times -4 is 20. -5 times -3 is 15. And then 15 again. Done. All right, now let's do the magnitude. Find the magnitude of vector V. That would be the square root of 5 squared plus -3 squared plus 5 squared. Okay, so we need to make that the square root of 25, and 25 is 50 plus 9, so 59. And that doesn't reduce at all, so we can just leave it right there. That's perfect. As far as I know, off the top of my head, I don't think there's any perfect squares that go into 59. All right, E. We're going to find a unit vector in the same direction as V. Now, a unit vector has to be unitized. You have to take your vector and make it smaller and make it the correct length. So currently vector V is the square root of 59 units long. So to make it a unit vector where it will be 1 unit long, you have to take vector V and divide it by the magnitude of V. So we're going to take 5, -3, 5, and we're going to divide it by the square root of 59. Which honestly, that's probably okay for writing it that way most of the time, but we will actually write it out. 5 over the square root of 59, -3 over the square root of 59, and 5 over the square root of 59. Now, interestingly enough, the problem said specifically it had to be in the same direction as V, and we did that. If you want to go in the opposite direction, it would have just been, let me just make a note. If you wanted to do opposite direction, it'd be U negative V, so opposite direction. And that would have been -5, +3, -5 over the square root of 59. Right? You make it so that your signs all switch, so that you're going in the opposite direction. So that would be, and again, this wasn't asked, it's just in case you're asked that kind of a problem, you know how to do it. Right? These two vectors are parallel because they are working in either the direction of V or the opposite direction of V. Let's keep going and do the next example. So we have a vector A, which is 6, 1, negative 3. It is not written in that notation, but that's what it is. And 1, negative 4, negative 2. So for part A, we want to find the magnitude of A minus B. So first thing we're going to have to do is we're going to have to find A minus B. So vector A would be 6I plus j minus 3k minus I minus 4j minus 2k. I'm going to keep it in that notation just so you guys get a sense of how this works. So it's 6I take away, well, here, let me do plus j minus 3k minus I plus 4j plus 2k, right? All of these signs switch. And then we combine like terms. So the two I components will go together. So it'll become 5I. The two j components will become 5j. And then the two k components will become negative k. Right, so these two went together. And these two went together. All right, so that's 5, 5, negative 1. All right, so now I want the magnitude of that vector. So the magnitude of A minus B would be the square root of the multiples of the components. So it's 5 squared plus 5 squared plus negative 1 squared. And that'd be 25, 25, and 1. So that's the square root of 51. And that would be the answer for A. Now for B, they want us to take 2A plus 4B. So that means we take 2 times 6I plus j minus 3k. And then we we add 4 times I minus 4j minus 2k. Okay, so we start with distributing, just like we would if this was an algebra problem. So 12I plus 2j minus 6k plus 4I minus 16j minus 8k. That would be 16I minus 14j minus 14k, right? Because again, we're combining the like terms. The k's are going together, the j's are going together, and the i's are going together. All right, last piece. Find a vector of length 5 in the opposite direction of B. Okay, that's a trickier problem than you might think. So to find this, you have to first find the unit vector in the opposite direction of V, or B. So that's step 1. Okay, so we need to find the magnitude of B. Well, we can just do it all at once. So the unit vector in the direction of B, in the opposite direction of B, so in the negative B direction, would be, I'm just going to bracket notation it, 1, well, I don't have to. Here, let me do it this way. It would be I minus 4j minus 2k divided by the square root of 1 squared plus negative 4 squared plus negative 2 squared. Well, that's 16 plus 4 is 20 plus 1 more makes 21. So that's I minus 4j minus 2k over the square root of 21. And that would be, oh, fiddle faddle. I actually did it in the direction of B. I didn't do the negative. I did the regular. That's okay. It's not a big deal. So I'll start with that. I'll start with this. So that's 1 over the square root of 21i minus 4 over the square root of 21j minus 2 over the square root of 21k. That's in the same direction as B. So now to do the unit direction in the negative B direction, it would just be negative 1 over the square root of 21i plus 4 over the square root of 21j plus, because it was minus, so we're going in the opposite direction, 2 over the square root of 21k. All right, so now step 2, you make it a length 5. Change to length 5 by multiplying. All right, so you take 5 times the unit vector in the negative b direction. So you multiply 5 times that negative 1 over the square root of 21i plus 4 over the square root of 21j plus 2 over the square root of 21k. And that would be negative 5 over the square root of 21i plus 20 over the square root of 21j plus 10 over the square root of 21k. And there you have it. We first made it length 1. We changed the direction, right? So I really found the unit vector in the direction of b is what I did. And then I made it the opposite direction. So if you want to call it, this is opposite direction as step 2. And then step 3 was I made it length 3. I kind of broke it down into 3 steps.